All right, so we're diving into the world of polymers today. Those giant molecules that are everywhere, with these excerpts from Polymer Physics by Rubinstein and Colby.
Yeah, it's interesting how for a long time scientists didn't actually know what polymers were.
Really, I mean, they are everywhere, like you said.
Exactly. Before the 1920s, they thought they were just groups of smaller molecules that were physically stuck together, what they called colloids.
And then, boom, Staudinger comes along with the macromolecular hypothesis, a total game changer.
Yeah, a huge shift. He realized that polymers weren't just hanging out together. They were actually linked by strong chemical bonds, these super long molecules made up of smaller repeating units, which we now call monomers.
So it's more like a long chain gang of molecules all linked together than a casual hangout.
Exactly. And the length of that chain, what we call the degree of polymerization, that's a big deal. A short chain versus a super long one, those act totally differently.
And we're talking millions of monomers long in some cases,
Yeah.
right? That's mind-blowing.
That's crazy, right? And here's where it gets even cooler. You can have the same monomer, but just change how they're connected, and you get different polymers. That's called isomerism.
So, like, you can use the same Lego blocks to make a car or a castle. It's all about how they're put together.
Exactly. Perfect analogy.
Oh.
Like polypropylene, the monomers can link up head to head, or even randomly.
And each way has its own, like, superpower, I'm guessing.
Exactly. The head to tail is the most common, and it makes the polymer more crystalline, meaning it's more ordered and rigid. The other ways are usually more flexible and less organized.
So, wait, two polymers could have the same chemical formula, but one could be like a rubber band and the other like a plastic fork, just because of how the monomers are arranged.
Exactly. A tiny change on the molecular level makes a huge difference. Polybutadiene is another one. It forms what are called structural isomers: cis, trans, and vinyl. And these isomers, they determine how stretchy it is, how it reacts to heat, stuff like that.
Okay, that's kind of blowing my mind, honestly. It's like this whole hidden world of complexity in materials we see every day.
It's a whole rabbit hole of cool stuff. And all these things, the type of monomer, the length of the chain, the different isomers, they all come together to define what we call the polymer's microstructure.
We've been talking about polymers made with just one type of monomer, like a one-flavor ice cream cone. But what about mixing it up?
That brings us to homopolymers versus heteropolymers. Homopolymers are the simple ones, made from a single type of monomer like polyethylene.
Like a big bucket of Legos, but only one type of brick.
Exactly. Then you have heteropolymers, which are made from multiple types of monomers.
Now we're talking. That's more like real-life Lego creations.
Precisely. And, fun fact, many important molecules in your body, like DNA and proteins, are heteropolymers.
Whoa, really? DNA with its 4 nucleotides and proteins with their 20 amino acids. So it's not just about synthetic stuff.
Exactly. This is fundamental. Now, let's think about how these long chains actually exist in space. We call this polymer conformation.
I'm already imagining them getting tangled like a bowl of spaghetti.
Haha, it's more organized than that, but you're on the right track. Imagine DNA, for example. Let's say each monomer in a DNA molecule is about a centimeter long.
Okay, I can picture that.
A single DNA molecule can be incredibly long. If each monomer were 1 centimeter, the whole molecule would be about 108 centimeters long. That's about a quarter of the distance to the moon.
Wait, are you serious? A quarter of the way to the moon?
Yeah, but here's the catch. That same DNA molecule can collapse down to a tiny volume, about 1 cubic centimeter.
How does something that long fit into something so small? That's like magic.
It's all about conformation. Imagine a long rope. You can stretch it out or you can coil it up. Polymers are similar. Their conformation, the shape they take, is all about flexibility.
So, like, how much can they bend and twist and turn?
Exactly. And this flexibility, plus how the monomers interact with each other and their surroundings, determines the overall shape of the polymer chain. These interactions can be attractive or repulsive, short range or long range.
Sounds complicated. Is there a way to actually visualize these different conformations? Like, well, what do they actually look like?
Great question. Figure 1.9 in the textbook has some good visuals. It shows different conformations, from a tight globule to a relaxed random walk, to a self-avoiding walk where the chain avoids crossing itself, all the way to a fully stretched out chain. And it shows them at different scales, so you can imagine them in a classroom, then across a campus, then through a city, and finally stretching to the moon.
Wow, I get it now. The scale is incredible. And these conformations, they can change depending on the environment, right?
You got it. Temperature, solvent, other molecules, all these things affect how a polymer chain arranges itself. Ready for a really cool concept?
Hit me. I'm all about cool concepts.
Polymer conformations often show fractal behavior.
Fractals, like those repeating patterns you see in nature.
Exactly. Like the triadic Koch curve. You start with a triangle, and with each step, you add smaller triangles to the sides, creating a pattern that looks the same whether you zoom in or out.
I can picture it. It's like each piece is a mini version of the whole thing. This applies to how polymers fold, too.
Exactly. How these long chains bend can create those repeating patterns at different sizes. We can measure this self-similarity with something called the fractal dimension, or D. It helps us understand the polymer's conformation in a new way.
That is so cool. Nature just loves using those repeating patterns.
It's a theme, for sure. Now, let's get practical and talk about the types of polymeric substances. We've talked about chains, but how do they form the materials we see?
Yeah, let's bridge the gap from those mind-bending chains to actual stuff.
Right. So first, we have polymer liquids. This includes polymer melts, which is what you get when you heat a polymer past its melting point, and polymer solutions, where the chains are dissolved in a solvent. Think wood protectants or floor polish. A lot of those are polymer solutions.
So those gooey liquids are filled with these long, twisty chains.
Exactly.
Yeah.
There's an important concept that makes polymer solutions different from solutions of smaller molecules, called the overlap volume fraction, represented by the Greek letter phi.
Overlap volume fraction. Okay, that sounds kind of intense. Break it down for me.
Imagine a dance floor. At the beginning of a night, there's plenty of space. But as it gets more crowded, you start bumping into people. It's similar with polymers in solution. Each chain has its space, and the overlap volume fraction tells us how much those spaces are overlapping.
So it's like a measure of molecular personal space.
You got it. In a dilute solution, the chains have lots of room, but increase the concentration, and their personal space overlaps. That's a semi-dilute solution.
Like a crowded party where everyone's dancing a little too close.
Perfect analogy. Yeah. Add even more polymers, and those spaces are basically gone. That's a concentrated solution.
So it's all about how much these chains are bumping into each other. This overlap volume fraction, I'm guessing it affects how the solution behaves.
It sure does. Viscosity, diffusion, how it responds to stress, all of that. Now let's move from liquids to solids. We've got two main types, semicrystalline and glassy polymers.
I'm guessing those names are a hint to how organized they are.
You're right. Semicrystalline polymers, like the polyethylene in plastic bags, have regions that are very organized, like tiny crystals, mixed with regions that are more random. Glassy polymers, like polystyrene in disposable coffee cups, have chains that are frozen in a disordered state.
Semicrystalline polymers like things neat and tidy, while glassy polymers are fine with a bit of a mess.
Exactly. And they each have their uses because of that. But wait, there's another type of solid, polymer networks. These are formed by something called cross-linking, where we use chemical bonds to link the chains together, creating a giant network.
So instead of individual chains, they're all connected like a giant spider web.
Exactly. Think vulcanized rubber in tires or silicone caulk. Both are examples of cross-linked polymer networks. Even Jell-O is a type of polymer network, just a very jiggly one.
We've covered a lot. How these chains are built, different arrangements, how they move in space, how they come together to form liquids and solids. It's clear that polymers are far from simple.
Incredibly complex, which is why they're so cool and useful. But there's another key factor, molar mass.
Molar mass. I vaguely remember that from chemistry. Refresh my memory. What is it and why does it matter for polymers?
It's crucial. Simply put, molar mass tells you how heavy a molecule is. And with giant molecules like polymers, that weight has a huge impact on their properties. Here's the thing. Most synthetic polymers, the ones we make, are polydisperse.
Polydisperse. It's like they can't decide what size they want to be.
That's a great way to put it. Polydisperse means that the chains in a sample don't all have the same molar mass. There's a range. Like a bag of pretzels, some are big, some small, but all pretzels. Unlike biopolymers, which are often monodisperse, meaning all chains are the same length, synthetic polymers have a mix of sizes.
A polymer party where all the chains are welcome, no matter their length.
Exactly. And this polydispersity, this range of molar masses, it really affects how the polymer behaves.
How do we even measure this mix of sizes? Is there an average molar mass?
Good point. We do use averages, but there are actually different types that highlight different parts of the distribution. The most common are the number average molar mass, Mn, and the weight average molar mass, μW.
Okay, two averages, M and μW. Why both? What's the difference?
Wow. Imagine you're calculating the average income of people in a room. MO would be like calculating the average per person, regardless of their income. MO would be weighting the average based on each person's income. People with higher incomes would have more influence on MIMPO.
Ah, I see. So M is a more general sense of the average chain length, while Membo emphasizes those larger, heavier chains.
You got it. And to describe how broad this distribution is, we use something called the polydispersity index, which is simply MOBO divided by M. A bigger polydispersity index means a wider range of chain lengths.
So a polydispersity index of 1 would be like everyone at that party having the exact same income, which is unlikely. A higher number means more variation in chain length.
Precisely. Now, how do we actually measure these molar masses? We can't just weigh them on a tiny scale.
Right, so how do scientists do it? It seems tricky.
It's not easy. We have several techniques, each with its own pros and cons. One of the tools we use is called osmotic pressure. It's based on something you might remember from chemistry, colligative properties.
Okay, colligative properties. Yeah, I think I remember that term. It's something about solutions, right?
Exactly. Colligative properties are those properties of a solution that depend on how much stuff is dissolved in it, not so much on what that stuff actually is. Osmotic pressure is one of those properties.
So it's not about the particles themselves, but like how crowded they are in the solution?
Precisely. Get this, osmotic pressure is directly related to MAN, that number average molar mass we talked about. It's kind of like with an ideal gas. The more gas particles you cram in a container, the higher the pressure. Same with polymers in solution. More chains means higher osmotic pressure.
Okay, that makes sense. So osmotic pressure gives us clues about the average chain length. What about that light scattering technique you mentioned? Does that involve lasers?
No lasers, but it does involve light. We shine light at a polymer solution and see how much gets scattered. The way the light bounces off the chains tells us about their size and shape, which is related to MELW, the weight average molar mass.
So light scattering gives us a peek at those bigger, more influential chains.
You got it. It's like they're putting on a show for us. Then we have intrinsic viscosity.
Intrinsic viscosity. That sounds like we're measuring how thick something is.
Not a bad way to think about it. Intrinsic viscosity tells us how much a polymer solution resists flowing, like honey versus water. Honey is more viscous because it's thicker, flows slower. With polymers, longer chains get more tangled, resist flowing more. So intrinsic viscosity is another way to get a MELW. It's simple, but we have to control the temperature because viscosity changes with temperature.
Okay, so we've got osmotic pressure for M light scattering and intrinsic viscosity for MELW. What about that last one-size exclusion chromatography SEC? What's special about that one?
SEC is the all-access pass of molar mass measurement. This technique gives us the whole picture, the entire distribution of molar masses from the smallest to the largest. We get MLW and even more.
That's awesome. How does it work?
Imagine an obstacle course for polymer chains, like
Yeah.
American Ninja Warrior, but for molecules.
Love it. So we're testing these polymer athletes.
Exactly. The obstacle course is a column filled with porous beads. Small chains weave through, easily taking their time. Big, bulky chains have to barge through, exiting faster.
So it's like a race where the slowest runner might actually finish last because they took the scenic route.
Exactly. As each chain exits the course, a detector records its size, giving us a profile of the whole molar mass distribution.
Wow. So with SEC, we get to see the whole range of polymer sizes in a sample.
Exactly. It's really powerful for understanding these molecules. But it's not just about measuring molar mass, it's about what that information tells us about how the polymer behaves.
It sounds like knowing a polymer's molar mass is like having a cheat sheet for predicting its properties.
Absolutely. Molar mass is like the control knob for so many polymer properties. Strength, stretchiness, how well it dissolves, how much heat it can handle. It's all connected.
So generally speaking, bigger chains mean a stronger, tougher material.
That's a good rule of thumb. Longer chains tangle up more, giving polymers strength. They also tend to have higher melting points and can be tougher to dissolve.
Makes sense. So if you're designing something like a new plastic, knowing the molar mass is key to getting the properties you want.
For sure. But it's not just the average molar mass that matters. Remember a polydispersity, that range of chain lengths? Well, that distribution is key for fine-tuning how a polymer behaves.
So sometimes you might want a narrow molar mass distribution where all the chains are similar in size, and sometimes you need a wider range.
Exactly. Imagine making a thin plastic film. You'd probably want a narrow distribution so the chains all pack together nicely. But for a rubber tire, you might want a broader range to get a balance of strength and flexibility.
It's amazing how much control we have over these materials by changing their molecular makeup. It's like fine-tuning a microscopic orchestra.
It really is. And this is just the beginning. We can create all sorts of crazy polymer architectures. Branch chains, star shapes, even things that look like bottle brushes.
Bottle brush polymers. Now that's something I need to see to believe.
We could do a whole other deep dive just on that.
Mhm.
But for now, let's get back to those conformations. Remember how we were talking about polymers behaving like fractals?
Oh, yeah. Those self-similar patterns are just mind-blowing. It's like nature's way of saying, look what I can do with a simple set of rules.
Exactly. Well, those fractal-like conformations have a huge impact on how polymers act in different situations, especially when they're dissolved in a solvent. Remember that overlap volume fraction thing? Well, polymer's conformation can change how much space it takes up in solution.
So a tightly wound up chain would take up less space than one that's all stretched out.
Got it. And that affects the viscosity, how easily things move through the solution, even how the chains interact with each other. It's like molecular social distancing. Sometimes they want their space, and sometimes they're okay with getting cozy.
This is making me see polymers in a whole new way. It's not just their chemistry, it's their shape, their size, even their social lives. It's like they're tiny machines with their own complex behaviors.
That's a great way to put it. And the more we learn about them, the more we realize how much more there is to learn. It's like exploring a whole new world at the nanoscale.
And we've only just scratched the surface. We've talked about plastic bags and tires, but polymers are showing up in all sorts of unexpected places.
They really are. Polymers are everywhere these days.
Yeah.
From medical devices to solar cells, they're truly the materials of the future.
It's incredible how far we've come from just wondering what these gooey substances even were.
It's pretty amazing. And honestly, the best part is that we're just getting started.
It's really amazing to think about how far we've come in understanding these giant molecules, from trying to figure out what they even were to now using them to create everything from self-healing materials to incredibly efficient solar cells.
It really speaks to human ingenuity and our endless fascination with how things work at the molecular level. And you know what? This is just the beginning. Really just getting started.
You've got me excited. What are some of the things you're most excited about in polymer science these days?
Oh man, where do I even start? One area that's just exploding is biopolymers and biomaterials. Scientists are using nature's polymers like proteins and DNA to create things like artificial tissues and organs, targeted drug delivery systems, and even biodegradable plastics that break down without harming the environment.
That's incredible. It's like we're taking inspiration from nature's playbook to solve some of our biggest challenges.
Exactly. And then there's nanotechnology, where we're manipulating polymers at the atomic level to create materials with totally new properties. We're talking about things like super strong and super light composites for aerospace, flexible electronics that can be woven into fabrics, and even tiny sensors that can detect tiny amounts of pollution in water.
It sounds like we're on the edge of a materials revolution, and it's all thanks to these amazing chains of molecules. But let's bring it back to the listener for a second. We've been on this wild ride through polymer science, but why should you, the listener, care? What's the takeaway message here?
That's a great question. I think the most important thing is to remember that polymers are way more than just plastic bags and toys. They're the building blocks of life itself, and they have the potential to change pretty much every industry, from medicine to energy to taking care of the environment.
So understanding polymers isn't just about passing a chemistry test. It's about understanding the materials that are shaping the world around us and the world we're creating for the future.
Absolutely. And who knows? Maybe this deep dive will spark an idea in your mind. Maybe you'll be the one to make the next big discovery in polymer science.
That's a great point. This episode has been packed. We've talked about everything from the basics of monomers and polymerization to those mind-bending polymer conformations and self-assembly. We even talked about how these amazing molecules are being used in life-saving medical devices and sustainable alternatives to traditional plastics.
And we've only just scratched the surface. The world of polymers is vast, complex, and full of possibilities.
So next time you see a plastic bag or a rubber band or even a strand of your own hair, take a second to think about the incredible world of polymers.
And never underestimate those long chain-like molecules. They might surprise you.
That's a wrap for this deep dive into the fascinating world of polymers. Thanks for joining us, and we'll see you next time.